For this lab, we were to observe an object moving at a constant velocity. The starting velocity and position can be used to predict the object's future locations with use of the momentum principle. If the object were moving at a constant velocity with no interactions, the final velocity would equal the initial velocity, and we could use it to plug into the position equation to be able to constantly update the object's position at certain time intervals. With the use of the program tracker, we can analyze a video of the object's movement and identify the initial conditions of the object. The tracker video records the ball's position at a specific time interval and outputs it into a table format. Based on this information, we can develop a VPython code for predicting the ball's movement under the ideas of no net force using an iteration process involving the velocity and position functions. We use this code to predict the ball's positions because it can give us precise locations with the idea that there are no interfering forces. A comparison between the experimental data and prediction data derived from the computational model should show no differences if the ball is moving at a constant velocity with no interacting forces. If the observed free-moving object is at a constant velocity, the predicted location should match exactly to the observed positions. The object moving in the video, serving as a system, is a tennis ball being rolled across the table. It appears that the ball is moving at a relatively constant velocity in the positive x direction. As you can tell in the video from the small line drawn on the upper coordinate line, I adjusted the axes of my tracker video so that the x-axis pointed in the upward direction, thus showing the ball moving in the positive x direction. Flipping the axes does not change the values but the direction of the movement of the tennis ball. All x values become y values and vice versa. If the axes were to be reversed, as if the positive x was then the negative x direction, the magnitude of the values would not change for reversed axes, just the sign. The computational model in VPython of the tennis ball was used to predict the ball's position if it were to truly be moving at a constant velocity. When the code is run, the visual representation of the data produces a sphere that mimics the motion of the tennis ball in the tracker video. The code is used to calculate updated positions of the ball at very small time intervals. This lets us be able to compare the model position of the ball against what was actually observed. When the computational model data is compared with that obtained from the tracker video, you can instantly tell that the graphs are not exactly similar. At first, the experimental tennis ball started out following the predicted graph data, but as more and more time passes, the two lines deviate, proving that there has to be an interacting force, or forces. The predicted model has a relatively straight line, whereas the observed model has a slight curve in the data you can see around 0.26 seconds. Because we know that the derivative of the position is the velocity, we can determine that the predicted model shows a more constant velocity because the slope of the line is constant, but the observed model curves, showing a less constant velocity. What I thought would be a fairly constant velocity of a tennis ball rolling across the table proved not to be when compared to a model example of what would show a ball of this nature moving at a constant velocity. This proves the existence of forces on the observed ball in non-ideal conditions. The graphs would be more similar if I had recorded an object that I knew had a constant velocity, such as a passing vehicle or something similar. The computational model created assumes that the net force on the tennis ball is zero, or that the interactions occurring add up to zero. Newton's second law does not give any information on how many interactions there are, just that when the interactions add up to zero, the velocity is constant. The graph that shows the actual versus the predicted positions of the tennis ball shows that the idea of the net force being zero is a good assumption, at least for the first few time intervals. The actual experimental run shows the ball is not gaining as much ground as the predicted model with the constant velocity. The tennis ball is obviously not moving at a constant velocity for the entirety of its path across the table, and that there is the possibility of an existing force acting on the ball.